and
Okay. So, okay, let me introduce myself and let me start my talk. So my name is Gansukh, as all of you know. And today I'm gonna talk about the reheating after inflation and with application to modified gravity. So the idea is that I will talk about how to use the reheating to put constraints on inflationary models that comes from modified gravity theories. Okay, and okay. So what we know is that probably you are already familiar with this figure here, and what we already know is that there are hundreds of inflation models out there in the market, which are which are very excellent and even consistent with the observational data. But the problem is we don't know how to break the degeneracies because many of them predict a similar prediction. For example, as you can see here, this gray, red, and blue contours are nothing but observational data. And then this purple, green, and yellow, and until this red one, there are inflationary models. The simplest model of inflation is based upon single scalar field, which is minimally coupled to gravity. So we have a Einstein-Hilbert term plus kinetic and potential energy for scalar field. And then, as you can see here, many of these models make a prediction based on the shape of potential. And among them, for example, this alpha attractor, which is nothing but this yellow one here, gives the same prediction as this R square inflation, which is nothing but R Einstein-Hilbert term plus R square. So there are some degeneracies. So that's something that we have to deal with. So let me also explain what is the inflation. So what we know when it comes to inflation, what we know is that, okay, inflation is an idea that our universe expanded rapidly or by exponentially. So this is the graph showing that. So we have a age of universe along x-axis, and we have the size of universe in a y-axis. Then inflation is the idea that the size of our universe expands by this amount, n to e to the 60 power or 10 to the 26 power within a very short amount of time, like 10 to the minus 35 seconds. So then this is accelerated expansion, meaning that this a double dot is positive. So this can be also equivalently understood by this dynamics of this scalar field rolling down to its potential. For this for inflation to happen successfully, like a universe expand like 10 to the 26 powers, there must have certain conditions must be satisfied. The first condition is that during inflation, the kinetic energy of scalar field must be subdominant to the potential energy. Potential energy is more dominant. That's how this scalar field can roll, and as it rolls, it can be the universe can experience exponential expansion. The second condition is that if the scalar field rolls slowly, then acceleration of scalar field is negligible compared to this so-called friction. So for this slowly rolling scalar field, we can write down equations of motion. The first equation is known as Friedmann equation, which comes from Einstein equation, and the second equation is nothing but the field equation. Then, if we consider or assume these two approximation into these equations, then we can solve these two equations and show that the Hubble parameter H is nothing but A dot divided by A, which is a constant during inflation. And which is, as I said, H is nothing but A dot divided by A. Then we can solve that for A, and we can show that this scale factor grows exponentially during inflation. So that is the basic idea of inflation. So yesterday we also, yeah.
I have a super question. So then when is potential free to do when inflation is?
Oh, okay. Then so inflation ends when this condition is no longer holds, meaning that the kinetic and potential energy becomes comparable to each other, or kinetic energy. Once potential becomes stiff, then scalar field rolls rapidly, so kinetic energy increases, and at certain point it surpasses potential energy.
Somewhere after then,
Yeah, somewhere around here, like that. Then this is a cheating sheet for slow roll inflation. It's made by Professor Sonchan Park from Yonsei University. And as we saw in the very first figure here, that actually when it comes to inflation, everything has to do with the potential. So the potential is very important, especially the shape of potential is very important in slow roll inflation. Then using this potential, we define so-called slow roll parameters, epsilon and eta. As you can see here, epsilon and eta, they are derivatives of potential with respect to scalar field. So meaning that it's something to do with the slope of the potential. Then to your question, inflation ends when these two parameters take a value equal to 1 or order of unity. Then the scalar field at the end of inflation is phi end, right? Then the amount of inflation is quantified, this quantity so-called number of E folds, like how many folds of E our universe expands, like 1E, 2E, and that is to solve so-called horizon and flatness problem, we need at least 50 or 60 E folds. That's why in this figure, we have these two ends of these predictions are the n equal to 50 and n equal to 60, because it's a required amount of inflation to solve horizon problem and flatness problem. Then density perturbation is order of 10 to the minus 5. And then these two are the most important observables of inflation. The first one is tensor to scalar ratio, which is nothing but related to amplitude of gravitation wave. And the second one is so-called spectral index, so which is how this primordial power spectrum tilted. And they are given in terms, these two parameters, observable quantities, they are given in terms of epsilon, and eta at the CMB value means that the number of E-fold is about 50 to 60. Then we use, again, this epsilon and eta, they are nothing but depends on potential. So using, for the given potential, we can calculate these two quantities and use observational data to test the particular inflation model. But the problem, as I said, there are degeneracies between models giving the same predictions, even though their nature is different. For example, again, let me mention one more time that alpha attractor is the potential is like hyperbolic tangent square, but the R square inflation is just a pure gravity model, but doing some conformal transformation, it gives the same prediction as alpha attractor. So staying in this dark blue region or staying around this means it's more consistent with observational data. So the question to ask is, so how to break these degeneracies between these different models? Then the question is, the answer is maybe reheating. I'm not sure whether reheating is the real answer or not, but it can help to break some degeneracies between models. Okay, then let me talk about what the reheating is after inflation. So let me just give some review. So reheating is the transition era. If you remember, there is a inflation ends somewhere around here, and the scalar field rolls down and oscillates around the minimum. But through this oscillation, the energy stored in inflaton field or scalar field can decay into standard model of particles and create a hot Big Bang in there. So that means reheating is a transition era between end of inflation and the beginning of radiation dominated universe. So during reheating, the energy stored in inflaton is converted into plasma of relativistic particles. So although there is no direct cosmological observable to test or to trace this period of reheating, but there are several models of reheating, some perturbative decay of oscillating inflaton at the end of inflation and non-perturbative process such as parametric resonance and resonance decay or even instant preheating. So actually that means having several different models means reheating is very much model dependent. So it's really hard to say what exactly happened reheating. But depending on model, we can estimate duration of reheating and the final temperature of reheating, meaning that the temperature of the universe, the thermalized, because inflaton decays into a standard model of particles and to this plasma, right? That means there, at the end of reheating, there will be some thermalized plasma, and we can estimate the temperature of that plasma, as well as its equation of state. Then we use those quantities to link it to the inflationary observables. Then the one assumption that we make in that process is we assume equation of state during reheating is constant. Then that means reheating can be helpful to break degeneracies between different inflation models that otherwise, overlap in their prediction of NS and R. So probably you are already familiar with this graph here. So we have 1 over AH. This is Hubble horizon of our universe. Oh, by the way, x-axis is scale factor or time, and y-axis is nothing but the wavelength comoving or the inverse of this is a k minus 1, inverse of wave number. Then during inflation, the horizon decreases. Then after inflation, it grows, and then modes that left the horizon during inflation comes back into the horizon. And then for this horizon exit and horizon re-entry, we can say that this wave number is nothing but equal to Hubble horizon at that time. Then, sure.
Horizon increases after reheating.
Why? Okay, horizon increases after inflation, basically, right? Okay. So because inflation is exponential growth of space-time, right? but the horizon is limited by speed of light, right? Then inflation is, since inflation happens in the space-time, so it grows much faster than speed of light, but the horizon is growing at the speed of light. So that means compared to the speed of light, the space-time itself is growing much faster than speed of light. So it looks like horizon is decreasing. But after inflation end, the space-time it still expands, but a much slower rate compared to the speed of light. So the horizon catches it up, and it looks it's growing. I think I can also explain. Yeah. Okay, then this inflation starts somewhere, and actually duration of inflation is counted from the end of inflation. So this is a NK here is a duration of inflation, and NTH is duration of reheating, and NRD is a duration of radiation domination, and so on and so forth. So since the HK is equal to K, we can write it in this way in this chain rule way. Like we can divide AK. We can write it like AK divided by AN divided by TH. TH is a thermal or a reheating. So if you these two can be canceled, these two can be canceled, and if you notice, this is just nothing but K divided by A naught and H naught. So then duration of reheating is nothing but the ratio between the size of scale factor of universe at the end of inflation over divided by scale factor of universe at the onset of reheating. So that is nothing but the duration of reheating. And again, as I said, we don't know how this universe evolved during reheating because it's a very model dependent. So it can be it couldn't be, a horizon can grow like this or like that or like that. So we don't know, but we can assume the energy density at the end of inflation can be related to that of at the end of reheating. So this is energy density at the end of inflation can be related to energy density at the end of reheating or at the beginning of radiation domination. So that means the energy density at the end of inflation and divided by energy density at the end of reheating can be expressed in terms of scale factor to some power of equation of state. So if we assume equation of state is constant during reheating, then we can estimate how much the reheating can last and what would be the temperature at the end of reheating. So this is the energy at the end of energy density at the end of inflation. The lambda here is nothing but kinetic energy divided by potential energy. Usually energy density is nothing but, for the scalar field, it's nothing but kinetic energy plus potential energy, right? Then if we factor out the potential energy at the end of inflation, then the kinetic energy at the end of inflation divided by potential energy at the end of inflation would be lambda effective here. Then on the other side, at the end of reheating or onset of radiation domination, the energy density, because it's a basically radiation dominated universe, so we can have this energy density at the end of reheating is nothing but proportional to the temperature of reheating to the 4. And this GTH is the number of relativistic degree of freedom at the end of reheating. Then we can, since AN divided by ATH is nothing but duration of reheating, so we can write the duration of reheating in terms of equation of state and also energy density ratio. Then we know what is energy density at the end of inflation from previous slide. Then, but we don't know what is energy density onset of radiation domination or at the end of reheating. So by assuming the entropy is preserved, meaning no entropy is produced after the end of reheating. This is a very much simplification, but we can make such a simplification. It's very strong, but we are here trying to make some rough estimation. So this is just an assumption.
If entropy doesn't change, then not thermodynamics.
Okay, it's also a very fair assumption, meaning that because the universe is kind of isolated system, right?
Could you repeat the question?
Oh,
I mean, the question would be better if one asks closer to the microphone.
Okay, let me repeat the question. So here I stated that we assume entropy is preserved, and the question was, what if entropy is preserved, then what would happen to the thermodynamics? That was the question. And now I'm trying to justify that since universe can be treated as an isolated system, and since it's an expanding, so if there is, okay, it's an assumption, but if there is no entropy produced, then it's just the volume increase, right? So anyway, okay, I will think about it, but this is just an assumption. Yeah.
Entropy is preserved or entropy density is preserved?
Entropy density, probably that is a better way to say it, I think. Yeah, entropy density is preserved. Then we, using this assumption, we can estimate the reheating temperature or the reheating temperature on set of radiation domination. Then since energy density of reheating is proportional to the temperature to the 4, we can use we can plug it there. And finally, we can write down a whole expression for the duration of reheating, which depends on equation of state during reheating. Then the wave number that we consider and the current value of scale factor and current temperature of the universe. Then the relativistic degree of entropy, then some inflationary quantities here. And this is HK is nothing but the Hubble parameter during inflation. And NK is nothing but the duration of inflation. So if you look at it here, we don't know much about these two degrees of relativistic degree of freedom of entropy and the universe, but we can make some particle physics assumption. Then according to particle physics, there can be about 100, but if we consider supersymmetry, then it's like 1,000. Then having obtained this duration of reheating, we can also estimate temperature of reheating by using this equation here, which is now the temperature of reheating depends on the duration of reheating, which is very trivial, and equation of state during reheating, then the pure factor coming from inflation. So then if we assume that this the degree relativistic degree of freedom is equal, then if we do some numerical values, then we will estimate that duration of reheating is nothing but 60 minus all the information coming that we can extract from inflation and the equation of state during reheating. So it's a relatively simpler. So then let me discuss some model. So reheating after inflation in minimal or standard model of inflation, like this setup. So because in the original title was a modified gravity, right? So now it's in the standard case. So when I wanted to discuss about the natural inflation, because natural inflation is now at the risk of being ruled out. So so this green and blue ones are the two different data. These are data, and these purple lines are the prediction of natural inflation with the potential given here, the cosine potential. And in this case, m is equal to 2k, m equal to 1k, sorry. Then if a potential is known, using that the cheating sheet that I showed, we can estimate what is NS and R. Then using that NS and R, we can plot this purple line here. Sorry, the gray line, the horizon, the diagonal gray lines. Then these gray lines depends on how many E-fold our universe can experience. So n equal to 50 line along this gray diagonal line, the value of this f changes from small to large. The lower one is small f, the higher one is a large f. Then these purple and these two purple correspond to E-fold equal to 50 and 60. Then, as I said, we can use this equation for duration of reheating and temperature of reheating. We can estimate, okay, for example, we know inflation should last about 50 to 60. So this NK is duration of inflation. Then basically this blue line here corresponds to purple line here. Sorry, it's correspond to gray line here. Then 50 to 60, they are here. Then using this NK, we can estimate what is N reheating. Then since we know N reheating, we can estimate temperature of reheating. But the thing is, we don't know what is equation of state during reheating. But we assume the equation of state is constant. So these the red, blue, black, and green, they correspond to different values of omega or equation of state. But the intersection point here, it corresponds to equation of state 1/3. Equation of state 1/3 means inflation ends, then radiation dominated universe starts, like instantaneous reheating. So the maximum reheating temperature is therefore this y-axis is a reheating temperature, and maximum reheating temperature is about 10 to 15 GeV. And I forgot to explain this. X-axis is nothing but NS, the same NS value here. And as you can see here, the NS, the prediction of reheating is staying in this yellow line is more preferred, meaning that if F value is 7, then we can have some consistent result some inflationary model can be first consistent with observational data, and also can give the prediction on the reheating temperature. But the problem is, even though NS is staying inside the observational data, but the tensor to scalar ratio, the y-axis here, is outside of reheat data, so it's not good. So meaning that natural inflation is kind of ruled out. But still, the good thing is that we can estimate reheating temperature for that model. So we now let me explain it for modified gravity model. So I will use the most general scalar tensor theory that Professor Yamaguchi mentioned it yesterday. And he also said that the Horondensky theory, which is known as the most general theory of scalar tensor theory, is nothing but equivalent to generalized Galilean theory. He explained it in a very nice way in his talk yesterday. And this first paper is Horondensky paper, and second paper is a generalized Galilean paper. And this paper, they show they are equivalent. And they then action is given in this form with L2, L3, L4, L5 in this way. And by choosing certain combinations of these G functions, the functions of scalar field and its a kinetic term, one can construct a broad spectrum of cosmological models describing inflation, not only inflation, but also dark energy. So since it's a very broad model, I can choose my favorite model. And this is my favorite model. And I choose these functions. The G2 is nothing but kinetic energy and potential energy of scalar field. Then I introduce some, some higher derivative term, plus, but still I keep the minimal coupling between Ricci scalar, the Ricci scalar and scalar field. So this is a constant. G4 is constant, which means the second term is sorry. If G4 is constant, then derivative of G4 with kinetic term is 0. So I ignore the second term. Then I consider also the G5 to be only a function of scalar field. So that means the first term survives, but the second term vanishes. So it's still simple, but still considers quite interesting model. So for this, using this model, I study natural inflation. So first, okay, here, okay, let me introduce one more thing. So what makes this model different from standard model is that I have this G3 and G5 in addition to this standard slow rolling model. So I call this G3 term or derivative interaction of scalar field as a alpha term. Okay, from now on, I will say alpha term, which is nothing but derivative interaction. Then I say there's a coupling between scalar field and Einstein tensor as a beta term. Okay. Then without this alpha and beta, what we have is just a standard single field inflation. And in that case, the natural inflation was in danger that we talked earlier. But if we have an alpha and beta term, we can save it. Not only to 2 sigma, but we can also save it even to the 1 sigma. So here, this the gray lines was corresponding to different values of f, but now these gray lines correspond to different values of delta. Delta is nothing but f is still the potential parameter. F and lambda, they are potential parameter. But also delta is the parameter that includes this alpha and beta term. Anyway, this figure shows that, okay, natural inflation can be saved in a modified gravity setup. Then this is a parameter estimation. So probably I think I can skip this part. Then this is a potential, and this is the shape of coupling function to make this kind of prediction. Then, okay, for this model, we can estimate the reheating temperature and duration of reheating and equation of state. So now I use, instead of previously I was using TH for reheating. From now on, I will use RE. So it's a change of notation, but everything is same. So we know since we fixed our inflation model, we know what is energy density at the end of inflation, and we know what is energy density onset of radiation domination. Then we know how these two energy densities related to each other through the duration of reheating. Then we use that everything to write down duration of reheating this way. Then we plot the duration of reheating on this upper panel here. The vertical axis is NS value, and horizontal axis is NS value, and vertical axis is duration of reheating. And the yellow region here, it is the best fit value of spectral index to the data. So the mean value is here. Then, as what we can see here is that the several different values of reheating can be several different values of equation of state during reheating can make a consistent inflation model consistent with data. For example, now this is a 1 sigma region of NS value, the yellow line here, and this red curve here is nothing but correspond to -1/3. The equation of state during reheating is -1/3. Then if we estimate the value here, we can translate it down and can estimate what would be the reheating temperature corresponding to that value, meaning that, okay, now at this intersecting point, the duration of reheating seems to be 10 E-fold. If reheating lasted this from here to there, if reheating lasted about 10 E-fold, then at the end of reheating, the temperature of the universe will be something around 10 to 12 or 10 to 13 GeV. It's quite large. Then if a duration of reheating is about, okay, let's say about 30, when equation of state is 0, then reheating temperature is slightly lower, like that. And this pink region is the EV electroweak energy scale, 100 GeV, and this is an MEV scale like that. Okay, then now we are using this reheating. We are combining the prediction of inflation with reheating in this figure. So we are already familiar with this graph here, and we're also familiar with this kind of graph here. This is a reheating temperature for different delta values. Delta values, different lines here. Okay, then if equation of state during reheating is -1/3, then we can estimate how much we can estimate the natural inflation and if equation of state is -1/3, the duration of inflation can also be constrained, and the maximum duration of inflation is then about the 56 E-folds. It's this line here, 56 E-folds in each graph. Then, depending on the reheating temperature and the equation of state, the duration of inflation is different in different cases. So that is what it shows. And so the prediction in the upper half plane means its equation of state is smaller than 1/3. So meaning that this red, blue, and black, they are equation of state smaller than 1/3. But when it becomes 1/3, it comes here, and that is correspond to this line here, meaning that if reheating ends instantaneously, inflation ends and a radiation-dominated universe it begins instantaneously, then maximum duration of inflation is just about a 56 EFOLs, like that. Then if equation of state is larger than 1/3, then prediction goes this way, and the larger duration of inflation is preferred. So that means we can use both the data from not an observational data, but some information from reheating and information from inflation, and we can use them together to put more tighter constraint on theoretical model of inflation. So this is the main idea here. So then, since I don't have much time, the second part, in the second model that I wanted to talk is about the Gauss-Bonnet theory. So even though this Horondensky theory doesn't explicitly show a Gauss-Bonnet gravity, but it has some equivalence with the Gauss-Bonnet Gauss-Bonnet theory, meaning that if we choose this G2, G3, G4, G5 in this way, X here is nothing but the kinetic term here, and Gz is nothing but some function of scalar field. Then if we use this form of choices for these functions, which gives the same equation as the theory with the Gauss-Bonnet term, with the coupling function Gz, meaning that they will give the same equations of motion. So that's why Horondensky theory, the Gauss-Bonnet theory, is a subclass of Horondensky theory. Okay, so this is the Gauss-Bonnet term. We have standard single field action, plus now we have a Gauss-Bonnet term with the coupling function Gz. Then we wanted to study how this additional term behave or evolve during inflation and reheating, but I will not talk about the second item. Okay, so that means, by the way, the Gauss-Bonnet term is topological, meaning that it is without this coupling function, it doesn't give any contribution to the equations of motion. Which we can see here. These are the equations of motion, the Friedmann equations and field equation. And if Gz is a constant, if this coupling function is not a function of scalar field, but a constant, then this derivative term vanishes. And then what remains is just what we know from single field setup. Then we can estimate NS and R, and we can put a constraint on it. And interesting thing that we wanted to emphasize here is that this NT, the spectral tilt of tensor power spectrum can be positive or negative. And we have NT is if the spectral tilt of tensor power spectrum is negative, then we call it red tilted. And if the tensor power spectrum is the NT, the spectral index of the tensor power spectrum is positive, then we call it blue tilted. So then we consider two models of Gauss-Bonnet inflation. And the one model, the models are here. We have a potential, nothing but the power law, and the coupling function, nothing but inverse power law. This is the first model. And the second model is like a little bit unusual, but it has some bump like this. But it gives a very interesting feature. I will explain it in the next slide. So we consider these two models. Then for these two models, the inflationary prediction is okay. There is no problem. Because this chaotic inflation model in standard setup, it's ruled out. But now, because of Gauss-Bonnet term or coupling function like that, it is now consistent with data. And it can also predict both red and the blue tilted spectrum. Then we study we estimate the reheating temperature and duration of reheating for this Gauss-Bonnet inflation. So first here we consider the power law potential with the inverse power law coupling function. And what we can see here is that compared to the standard case, the black one is the standard case without Gauss-Bonnet term. Compared to the standard case, reheating temperature in Gauss-Bonnet inflation is slightly increased. This is what we noticed. And this is for this model. And okay, I think I can skip this because it's not that important. The second one is we consider this model, which predicts a blue tilted spectrum. And blue tilted spectrum is actually important when we study primordial gravitation waves. But in this work, I didn't include, in this talk, I didn't include gravitation waves. So I will just introduce model. So for this kind of hyperbolic tangent potential and this kind of hyperbolic sinh coupling function, still we have enhanced the reheating temperature, and we can still estimate the duration of reheating and temperature of reheating. I think that is what it is. So thank you for your kind attention. I will stop here. So let me summarize what I did. So the main summary that I wanted to give here is that we can make some assumption like a constant equation of state during reheating, and also no entropy production after end of reheating. And making such assumptions, we can estimate duration of reheating, temperature of reheating. Then we use that information to put tighter constraint on inflation. Usually we do things from the other way around. We set up a model and we estimate how long inflation lasts and what is temperature energy of inflation. But now I'm saying that we can use such information from reheating to put the tighter constraint on inflation. So this is the main idea that I wanted to deliver. Okay, thank you. So maybe I can have questions if you have. Okay, thank you.
Hello, Gansukh.
Yes.
So you introduce several models.
Yes.
After you do this kind of constraint,
Sorry?
what is your opinion regarding these models? Which one is your preference? You think which one is more promising? Better?
Oh, okay.
Based on the constraint.
Okay, the one thing is that when it comes to saving some inflationary models, the modified gravity models of inflation seems to be interesting, and also those models can have some interesting consequences in the late time universe. And it's still hard to favor some model over the others. So I probably cannot answer for that part of the question. So Do you understand what I mean?
Yeah, yeah. I mean, this is quite normal to the modified.
Yeah, yeah. It's
activity theory. There's no clue.
yeah, yeah. That's right. That's right.
You said that this reheating process can remove some geometry of this inflation model.
Yeah.
But your result looks like it increases degeneracy.
No, it
is ruled out, but if you consider reheating, then it also come into the consistency.
yes, yes. Okay, the question was, even though I said reheating can help to break degeneracies, but it looks like it's adding more degeneracies. So my answer is not really. It looks like it's adding more because there are some models were already ruled out, right? But we are bringing them back into the game. It looks like we are adding more degeneracies. But for example, if in here, in this model, there are using this reheating information, we can put the tighter, because even though we say, 50 to 60 fold, right? This is this value range is itself is already put too much degeneracies. But if we know the reheating temperature precisely, then we can put exactly how long inflation can last. For example, in our case, in instantaneous reheating, it's just a 56, no more than that, or no more, no smaller than that. But here it was without this reheating information, it was, the wide range of n, the number of evolved was allowed, but now.
So this reheating, if we consider reheating, then it gives very strong concentration duration of inflation.
Yeah, like that. So because why I use the reheat, the natural inflation is, of course, I wanted to save it by introducing a modified gravity model, because just to show that modified gravity models can, save this kind of model. Then even there are some models, for example, Starobinsky inflation, right? Or okay, let me say R square alpha attractor, which is hyperbolic tangent. Even without the modified gravity setup, it is already consistent with observational data, right? But if we use a reheating information, we can put a tighter constraint on how long exactly these alpha attractor models should last. That is how to break degeneracies like that. Yeah. Okay. Is there any other question?
So at the beginning, you said that modified potential plays important role.
Yeah, yeah.
Then maybe modified gravity theory is not quite significant because it's I don't know.
Not really, because for example, here, let me see here. Usually, yes, you are right. I said the potential is important, right? But the modified gravity corrections introduces some effective potential.
Okay.
So even though I use for example, here I use the power law potential, this inverse power law coupling function makes effective potential different from power law, such that the effective potential shape makes inflation more interesting like that. Do you understand what I mean?
Yep.
Yeah, okay. Okay, if there is no other question, then I will end my talk here.